Now it's visible. Is it okay?
No, sir. Yes, sir.
Okay, so now you go for see how to classify the different structures, whether it is spinal or it may be inverse spinal. So for that, see, you can have a molecular formula is you can say it's a AB2O4 type structure with molecular formula AB2O4 type, and for that it may be say M3O4 type oxide or it may be AB2O4 type. That means there are 3 metals and 4 oxygen is there. So see, out of this 3 metals, you can have a suppose formula is AB2O4 in which one is metal is in a +2 oxidation state and other 2 metals are in a +3 oxidation state. So you can have, sorry, 2 metals are in a +2. That means A is in a +2 state, and metal B, one B is in a +2 and other B is in a +3. This is the oxidation state. Sorry, all this B are in a, you can say, +3 state. So one metal is with a +2 and other 2 metal with +3 state. In this way, see, this is the M plus एक मेटल है जो वो +2 स्टेट में होगी, दूसरी 2 मेटल्स है वो +3 में होगी. So now see, out of this 3 metals, so how they take which positions, they occupied in a which void in a lattice structure. On the basis of that it is classified. So if here metal is occupied, A+2 is occupied in a tetrahedral void, it is in a tetrahedral void, and B+3, so both the B+3 are there in a octahedral void. 100% octahedral void is occupied by B+3 and 100% tetrahedral void is occupied by A+2. So such case we call it is as a normal spinal structure. For example, see, you can have a formula MgAlO4, Al2O4. Here see, or you can have a Mn twice O4, or you can have a Zn Fe twice O4. So all in all this case, even in FeCr2O4, in all this case, what happens? Even in FeCrO4. So here see, in the first case, see, magnesium is in a +2 state. If you go for MgL2O4, so where Mg+2 is there and Al+3 is there. So Al+3 occupied octahedral void and Mg+2 is occupied tetrahedral void. In a second structure, Mn3O4, one metal is in a +2 state and other two is in a +3 state. So Mn+3 occupied octahedral void again. +1 +2 is in a tetrahedral void. Similarly, in case of ZnFe twice O, so you can have a Zn+2 and Zn+2 and Fe+3. So Fe+3 is there in octahedral and this is in a tetrahedral void. So this is called normal spinal case. Okay, this is a normal spinal. Here see Fe+2 is there and 2Cr+3. So this is in octahedral void and this is in a tetrahedral void. In short, +2 metal is in a tetrahedral void. So this is you can called normal spinal. And ये example आपको याद रखने हैं. Okay. ये कौन से state oxidation ऐसे जो examples है उनका structure it is of case it is belongs to spinal. Now सी दो Fe वाले जितने स्ट्रक्चर से वो इनवर्स स्पाइनल्स में आएंगे तो ऑटोमेटिकली आप उसको डिफरेंशिएट कर पाओगे. द सेकंड केस व्हिच इज द केस ऑफ इनवर्स स्पाइनल स्ट्रक्चर. सी व्हाट हैपेंस इन द इनवर्स स्पाइनल स्ट्रक्चर. In the case of inverse spinal structure, you can have a see if the structure is inverse spinal, then what happens? Second type of structure is inverse spinal. So what is called inverse spinal structure? So see, in the case of inverse spinal structure, you can have a molecular formula is again same M3O4. Molecular formula is a M3O4. So M3O4 in which, see again you are having three metals. So with this formula, one metal is in a +2 state and one metal is in a +3 state. So see +3 metal. Here see plus, or you can say +3 metal is there 50% in a tetrahedral void and 50% in a octahedral void. That means one metal is in a tetrahedral, another one is in a octahedral. In a 50-50% distribution is there, and +2 metal is there in a octahedral void. So this is we call inverse spinal. Or so its example are, or you can have a CAB 2O4 type structure. So A +2 is there in a octahedral void, and B +3, one B +3 is there in a tetrahedral void, and other B +3 is there in a octahedral void. So this is you can call it inverse spinal. Its example are Fe3O4 magnetite, where two Fe are there. One is Fe +2 and other two are there in a +3 state. So out of these, Fe +2 is occupied in a octahedral void, Fe +3 is occupied in a, one is in a tetrahedral void and another one is in a octahedral void. So this is you can call it inverse spinal structure. Similar, see other ferrite salt are there where Ca Fe twice O4, or you can have a nickel Fe twice O4. So here see Ca +2 is there and two Fe +3 are there. So what happens? Ca +2 is occupied in octahedral void and Fe +3 is occupied, one is in tetrahedral, another one is in octahedral void. Again see nickel Fe twice, two Fe containing compounds are there. They are belongs to example of this type of structure. So here see you can have a, one is Fe +3 which is in octahedral, another one is in tetrahedral, and nickel +2 is belongs to octahedral. So this is the case of inverse spinal. Okay, so you know the difference between normal spinal and inverse. Normal spinal case, what happens? A +2 is there in tetrahedral and A +3 are there in octahedral. But in the case of inverse spinal, so +3 structure 50% is in a tetrahedral and 50% is in a octahedral. Okay, is it clear? Is it okay?
Yes, sir.
Okay. So third case is, that is called defect spinal. What we call say defect spinal structure. So metal is not in a stoichiometry is not mentioned for it is not maintained. So for example, see if you having aluminum 0.75, nickel is 0.25, and this both belongs to tetrahedral, and another one is nickel is 0.75 and aluminum is 0.25. This part belongs to octahedral void with O4 oxide. So see this type of structure is you can call defect spinal. Even one of them example is Al2O3 also. Gamma Al2O3 is also example of defect spinal. So in this way, there are three types of the structures: spinal, you can say normal spinal structure, inverse spinal, and defect spinal. So how, using CFSC, you can predict whether given structure is a spinal or inverse spinal? How to predict it? So see, this is predict in this way, on the basis of crystal field stabilization energy, predict whether mn-twice O4 and Fe-twice O4 are spinal or inverse spinal. Experimental value is given CFSC, or experimental value for crystal field stabilization energy is, it is, you will be given the experimental value, it's a minus 0.26 octahedral splitting for Fe3O4. Okay, similar way, another case it will be also given to you. Sorry, it's a minus 0.4 octahedral splitting. This is given to you. Experimental value is given. So now what you can do? So you can do the CFSC calculation. Okay, what you can do? You can do the CFSC calculation and compare with this one. Similar way, for Mn to 304 it is given. Now suppose we assume that structure of Fe3O4 is normal spinal. And what happens? 1 Fe plus 2 is there in which void? What is, which void is it is there? If it is normal spinal, then what happens? What is the arrangement?
Tetrahedral.
Yes, Fe plus 2 is there in a tetrahedral void, and 2 Fe plus 3, which are there in octahedral void. So what you can do? You can compare with this one. See, first one is, it is there in tetrahedral, and 2 Fe plus 3 is there in octahedral void. So see, in tetrahedral geometry, which orbital fill first? It is EG or T2G?
In tetrahedral, EG will be filled first.
Yes, E orbital is filled first, E orbital, and in T2 orbital is filled later. So what happens? You can have a C6 Fe plus 2 means it's a D6 system. So you can have a 6 electrons. So these are filled in this way: 2, 3, 4, 5, and 6. Okay, so what is this crystal field stabilization energy? 3 electron multiply with energy of E orbital is decreases by
6 dq minus
6
60.
dq. So it is minus 6 into 3. This is by minus 6 dq, or you can say octahedral 0.6. It is a 0.6 octahedral. Minus 0.6 octahedral, okay? And energy of T2 orbital is increases by 4 dq, so 3 into 4 dq, 4 octahedral, 0.4. So you can have a 6 into 3, 1.8 minus and 12, 1.2 plus. So net answer become minus 0.6 octahedral. Similar way, see if it is arranged in Fe plus 3, then which orbital fill first? If it is in octahedral void, then Fe plus 3 is a D5 system. How it is it gets filled? What happens?
सर इसका CFSC तो 0 हो जाएगा ना D5 पे.
हाँ D5 है तो आप फिल है completely, so इसका 0 हो जाएगा definitely. So what happens? How it is filled? Three electrons in a P2G and 2 electrons in a PG set. So you can have a what happens? CFSC is 0. For octahedral it is 0. Now see how to convert see this is a 0.6, so you can how to convert it into octahedral. So what is the relationship? This is your tetrahedral, okay? This is not the octahedral, sorry. This is a tetrahedral. So what is the relationship between octahedral and tetrahedral? It is a
4/9 octahedral.
yes, octahedral. Yes. So one tetrahedral equal to 4/9. Good. So tetrahedral is equal to, you can have a 4/9 octahedral. So you can here see simply put the value instead of tetrahedral. See, one tetrahedral is equal to 4/9 octahedral. So total crystal field stabilization energy, this is a tetrahedral. So it is equal to minus 0.6 tetrahedral. There you can put here 4/9 octahedral. Okay. So what is your answer? It's a 2.4/9, that is minus 0.26. This is your answer. Crystal field stabilization energy. This is your answer. Okay. So this become your answer. So what you can do here, you have calculated by 3 into minus 0.6 tetrahedral plus 3 into 0.6 and 0.4, you can say tetrahedral. So you can have a, this is in a tetrahedral unit. So you can have a net answer is this one. So this is the value. Okay, now same you can calculate for which structure? Same calculation you can do for inverse spinal. If the structure is inverse spinal, then what happens? If structure is inverse spinal, then you can have a
half octahedral and half tetrahedral FHC plus.
it is a half
Octahedral and half tetrahedral FHC plus.
Okay, it is a half octahedral and half tetrahedral. So here you can have a it is arranged in this way. CFE plus 2 is there in which void? See here, O minus 2 is arranged in FCC, or you can say in CCP arrangement. Now see, Fe plus 2 metal is in a Fe plus 2 is in a octahedral, and Fe plus 3 is in a, one is in a tetrahedral, and one Fe plus 3 is in a octahedral. So for Fe plus 2, that is which system? D6. How in octahedral field it is arranged? This is T2G and EG. So 6 electrons are there. So these are the 6. Okay. So what is it crystal field stabilization energy for this one? 4 into 0.4 is minus 1.6 octahedral, plus 2 into 6.6 is 1.2. What is your net answer? Minus 0.4 octahedral. Okay. Is it okay? Okay. It is okay. Is it okay?
Yes, sir.
Okay. Now in Fe plus 3, it is D5 system. So again, see, it is, what is CFSC? E2G, and this is EG. So it become 0. If you're having tetrahedrals, then it's a E orbital field first, and you can have a T2 orbital field later, but it is again half field. So in both the case, it is 0. So total CFSC is minus 0.4 octahedral. This is matched with which one? Experimental value. This is matched with the experimental value. Okay, and therefore it is which structure? It is matched with experimental. So your structure is inverse spinal, because your calculated data is matched with theoretical. Is it okay? In the same way, you can go for Mn3O4. What happens? What you can do? Mn3O4 hai. So one is Mn plus 2, another one is Mn plus 3. This is the normal spinal, so we directly go for, this is in a tetrahedral and this is in a octahedral. It is a normal spinal, इसको prove करते हैं. So tetrahedral means it's a D5 system and this is D4. So D5 system में क्या होगा? कितना आएगा CFSC? 0. What happens in D4? So it says CFSC become equal to 3 into minus 0.4 octahedral plus 1 into 0.6 octahedral. So it become 0.6 plus 1.2, that is 1.8. Sorry, 0.6 plus, you can say 0.6 minus 1.2. So it's a minus 0.6. So this is a calculated data. This is matched with the theoretical or practical if it is provided. So you can have again see, so you can prove that this structure become normal spinal. Okay, दोनों possible calculation है वो आपको करना है. Of course, see, this is here you can have multiply it with 2, because 2 such Fn plus 3 are there, so it's a minus 1.2, and this is matched with the given experimental data. So you can have you can prove whether it is normal spinal or it may be inverse spinal. Is it okay? This concept is clear, so we move to the next one.
Yes, sir.
Okay, fine. So this is a very important, one of the very important concept. Now after that, so then next we move to the isolable analogy. Whether given structure is lobal or you can say it is isolable. And then we go for color spectra. So isolable principle. What happens in the isolable principle? So see, this is parallel. This parallels between organic and inorganic fragment was first described by
18
this is
electrons and 8
yes parallel relationship between organic and inorganic fragment was first described by Roald Hoffman. According to this concept, the fragment of cluster are deemed to be isolable if they possesses same number of frontier molecular orbital FMO with similar shape symmetry and radial extent. Second one is approximately similar energy. So you can have a say approximate similar energy and same number of electrons are available for cluster bonding. Same number of electrons are available for cluster bonding. So you can say that these two structure may be whether it is isolable. So better way is see how to you can decide it. Isolable pair. So see types of the complex is suppose transition metal complex and organic fragment. So you can have a see transition metal complex. And its electron. You can compare with organic fragment. Or you can say p block element. With its number of electrons. So you can have a see electrons from organic part is compared with electrons from inorganic part. So suppose the structure type is ML2 type. So ML2 type structure is there. It is having 4 electron and 2 ligand type structure. So it is isolable to carbon, and carbon belongs to C14 group. So it may be carbon, silicon, germanium. Boron belongs to 13 groups. So BH having 4 electron, 3 plus 1, that is 4. That is from organic side. You can have a 4 electron, and from inorganic side you can have a 15 electron.
14.
Then 14 electron. Then you can say that these two are isolable with each other. Okay, in order to getting isolable structure. So electrons from organic part and electrons from inorganic part. So that is, you can compare. So depending on that electrons, you can predict whether these two are isolable or not. Organic part electron is 10 higher than 10 less than that of the inorganic part. Now next, you can go for, see, suppose your structure type is ML3 type. So it is isolable with, see it having 15 electrons, then it is isolable with
Nitrogen.
CH,
Group 15.
carbon,
Group 15.
4 plus 1, that is 15. B boron है तो BH, 2 लगे, so 13 plus 2, it is 15. All the p block element, nitrogen, phosphorus, arsenic, antimony, okay. So they contribute 5 electron. Similar way you can have a, suppose complex is ML4 type, then how it is it is contribute 16 electron from inorganic part. It is isolable with
16 element.
CH2, or you can have a BH3, 16 electron, or you can have a suppose 15 group element, so NH, or you can have a 16 group oxygen, sulfur, selenium, all they are. They contribute 16 electron, 6 electron. So they contribute 6 electron. Now then complex is ML5 type, which having 17 electrons, so it is isolable with CH3, 4 plus 3, 7, or you can have a OH, oxygen is a 16 group, so OH, 16 plus 1, 17, SH, all the halogen. So they give 7 electrons.
Sir, NH2 will be also there.
One sir?
NH2?
NH2 of
amide.
course is there, yes,
NH
yes.
minus
NH,
होगा.
नहीं, minus नहीं, simple neutral NH2 है, so you can take it. Okay. चार्ज नहीं लिखते हम, सिंपल NH2 है तो यू कैन टेक इट, NH2 माइनस नहीं आएगा, सिंपली NH2. ML6 टाइप कॉम्प्लेक्स है तो क्या करेंगे, 18 इलेक्ट्रॉन है तो सामने 8 इलेक्ट्रॉन होने चाहिए, सो CH4, यस, तो ऑर्गेनिक पार्ट इज CH4, and you can have a xenon, krypton, okay, all these 18 group element, they contribute 8 electron. So this is the way you can predict which two are isolable with each other. For example, see if you having FeCO 4 times, So this complex is which type of complex?
16.
Ml4.
16 electron. 16 electrons.
So it is has 16 electrons. So you can have a say 16 electron, and opposite fragment you required is oxygen, that is having how many electron?
6.
6 electron in the outermost shell. So you can take this one. So what happens, see here, oxygen having 6 electron. So you can have a Fe is there. So Fe's oxidation state is 0. So Fe's atomic number is 26. So Fe contribute 8 electron. Outermost electron is the electron of 4s and 3d orbital. 4 ligands are there. Each ligand contribute 2 electrons. So 2 into 4, that is 8 electrons of CO ligand or CO. So you can have a total 16 electron. So it is isolable with oxygen, or you can say CH2. Okay, it's whatever. So see what happens in the case of CH2. You can have a 2 hydrogen
6 electrons.
and 2 radical, 2 electrons still left. Okay, this type of this structure. You can go for structure of Fe, CO4. So you CO utilize out of 6 इलेक्ट्रॉन 4 इलेक्ट्रॉन. Fe के पास टोटल 8 इलेक्ट्रॉन है. फिर Fe के पास टोटल 6 इलेक्ट्रॉन है. It is in the you can say it is in 3d orbital. Fe plus 2 है तो 3d6 होगा. अब इसका जो इनका जो टोटल स्केलेटल इलेक्ट्रॉन है, that is how to getting skeletal electron. So this is simply by C minus V plus X. That is the charge. Or if you don't want to use this formula, then simply see this. You can write down its structure of Fe with
26
structure of
electrons.
26. Yes. It is at having 26. तो यहाँ कितने 4 CO है, कितने यूज हो गए? 8 electrons. It's a pi acceptor. Okay. Here otherwise you can have a C. Of course it is 8 electron minus V is a, oh sorry, C is a, you can say it is having 16 electron. You can remove this formula, no need to go for this one. और इनका आप स्ट्रक्चर कंपेयर करोगे, सो इट इज सिमिलर टाइप स्ट्रक्चर्स होने चाहिए. यहाँ Fe CO इज अ पाई एक्सेप्टर और डोनर, इट इज अ पाई एक्सेप्टर. ओके, CO के पास 4 CO है तो कितने इलेक्ट्रॉन हो गए टोटल? 8 इलेक्ट्रॉन 4 CO के हो गए. और Fe के इलेक्ट्रॉन्स जो है वो कुल मिला के इलेक्ट्रॉन्स कितने हो गए? Fe के जो अपने इलेक्ट्रॉन्स है वो सारे इलेक्ट्रॉन्स आप देखेंगे तो इसमें से 4 CO ऑलरेडी ज्वाइंट है. बाकी बचे जो Fe के इलेक्ट्रॉन्स, Fe के तो 3D सेल में 6 इलेक्ट्रॉन है. आप 3D में चलो पेयरिंग होगा, एक इलेक्ट्रॉन CO का एक्सेप्ट करते रहो तो 6 इलेक्ट्रॉन 3D में है. Fe का जो स्ट्रक्चर है उसमें 4s2 पैक है, 3D 6 है, तो D ऑर्बिटल में 6 इलेक्ट्रॉन है. सो आउट ऑफ 6 सी ये CO जो एंटर करेगा वो अपना इलेक्ट्रॉन, बाकी की जो 4D में 4 CO अपने डोनेट करेगी एक एक इलेक्ट्रॉन, समझ लो. तो 6 में से 4 D ऑर्बिटल के इलेक्ट्रॉन यूज हो जाएंगे. कितने बाकी रहेंगे? 4 इलेक्ट्रॉन है ना, D ऑर्बिटल में 6 है, ऐसे है. तो 4 जो है ये हाफ फिल, उसमें एक एक इलेक्ट्रॉन आ जाएगा तो वो पेयरिंग हो जाएगा. तो बाकी कितने बचे लोन पेयर?
2 one loop
तो यहाँ पे से आप उसको ऐसे ड्रॉ करोगे तो दिस टू स्ट्रक्चर आर लाइक क्वाइट सिमिलर, दे आर हैविंग सिमिलर शेप और यू कैन से सिमिलर ज्योमेट्री, और वैसे भी आप इलेक्ट्रॉन काउंट करोगे तो इनके 6 हो जाएंगे, इनके 16 है। सो दे आर कॉल्ड आइसोलोबल विथ रिस्पेक्ट टू ईच अदर। ऐसे ऐसे नंबर ऑफ क्वेश्चंस है वो नेट एग्जाम में भी पूछे गए हैं। प्रीवियस ईयर के आप पेपर देखोगे तो उसमें जैसे आइसोलोबल क्वेश्चन के इनके रिलेटेड क्वेश्चंस है। नेट एग्जाम में ऑलरेडी इनके क्वेश्चंस पूछे गए हैं। जैसे आपको सपोज इनको जो डिफरेंट एग्जांपल्स है उनका कंपेयर करना है, सो आई विल गिव यू वन मोर एग्जांपल्स, यू कैन हैव a see. Suppose structure is cobalt CO4 times. So this is again isolable with which one?
group 17.
You can check it. First calculate the electron. Electron पहले देखना, उसके बाद इलेक्ट्रॉन एंड लिगेंड दोनों मैच होता है तो बेटर रहेगा।
9 and 8 is total 17 electrons here. So it will be matched with group 17.
17. So see in this case what happens? Now here you can have a CO is a D7. Okay. So it is, you can say CO atomic number is 27, तो इनके 9 इलेक्ट्रॉन हो गए, 4 लिगेंड है तो उनके 8, तो टोटल 17। सो सामने आपको 7 इलेक्ट्रॉन वाला ऑर्गेनिक स्पीसीज चाहिए, वो कौन सा रहेगा? इट में बी CH3, इट में बी NH2, it may be OH, FCl. Okay, so these are the isolable with respect to each other. These are the isolable. So in this way you can calculate. Suppose you are given CP, cyclopentyl is a 5 ligand, 5 electron contributor ligand, MO, CO twice. What happens in this case? So molybdenum है उनके पास 40.
So what is code number CP here? Cyclopentadiene here.
It's
1 or 5.
It's a 5, FTCT 5. कुछ दिया नहीं है तो आपको 5 कंसिडर करना है। ओके, अदरवाइज FTCT इज गिवन। और वो हम मेटल कार्बोनिल और मेटल नाइट्रोसिल यूनिट लेके उसमें ज़्यादातर डिटेल में जाकर क्लियर करेंगे। सो व्हाट इज एटॉमिक नंबर ऑफ मोलिब्डेनम? इनका जो
60.
एटॉमिक नंबर है उसमें से आपको क्या करना है? इट इज
Tungsten group में molybdenum है।
मोलिब्डेनम बिलोंग्स टू टंगस्टन ग्रुप।
molybdenum.
यस, इनका जो एटॉमिक नंबर है वो 42 है। कितना है? 42। सो आगे वाला जो क्रिप्टोन है वहां तक पे एक्सेल होगा। सो आप 36 माइनस कर देंगे, सो यू विल गेट 6 इलेक्ट्रॉन। सो 6 इलेक्ट्रॉन फ्रॉम molybdenum plus 5 electron from cyclopentyl ligand and 6 electron from 3CO. So total कितने इलेक्ट्रॉन हो गए? 70. So it is also isolable to all this. Okay. Is it okay?
Yes, sir.
Okay, so this is again very important concept. That is second concept, isolable principle. Now we go for different type of transitions, or you can say how you are getting the color. So colored applications, which complex shows which type of the color. Okay, so how which color is absorbed, then which color is reflected. So all this is decided using, you can say, particular method.
42 minus 36 कैसे हुआ?
Yeah. Hello.
42 minus 36.
42 माइनस 36, आप देखो इनका इलेक्ट्रॉनिक कन्फिग्रेशन लिखोगे मोलिब्डेनम का, तो क्रिप्टोन तक वो पैक सेल है, उसके बाद आएगा 5s2 4d4, तो ये 6 हो गए। जैसे आप 3D सीरीज के एलिमेंट का लिखते हो तो उसमें आर्गोन 18 तक पैक आएगा, इसलिए हम 18 माइनस कर देते हैं और 4s2 3d काउंट करते हैं इसी तरह। Is it okay?
Yes, sir.
Okay, fine. So next we go for color spectra, how you are getting color property. Color properties of transition metal. So complex shows color because of the DD transitions. Complex so color because of DD transition. And see, DD transition is a Laporte forbidden. DD transition is Laporte forbidden. So DD transition are less intense. DD transitions are less intense. So what you can do?
Sir,
Yes.
at first Laporte allowed comes, then Laporte forbidden, then spin allowed, then DD transition.
First is Laporte transitions. Yes. Then
Yes,
spin.
then Laporte forbidden, then spin allowed, then DD
Yes.
transition. Intensely
Yes.
color.
Yes. But see, we are talking the Laporte is a forbidden. See, DD transitions तो उस केस पे Laporte forbidden आएगा, और यहाँ कलर जो है because of the D electron transitions करता है उससे मिलता है. Okay, and DD transition is purely it is Laporte forbidden. So what you can do here, you can have a specially can go for DD transitions are less intense. Okay, so you can go for absorption band. That is from light absorption from visible region. This color is because of the visible light, or you can say white light. Priority order is of course is this one whenever you are checking. Okay, so now see, this is from a particular, you can say visible light, or you can say white light. So you can have a VIP gear. The white light is composed of all this color, that is violet, indigo, blue, green, yellow, orange, and red. So suppose material is exposed in visible light. So it absorbs all color. So what happens? All absorb. Why we are getting see color spectra? Because of particular reflection light. Okay, reflection light is a particular color. So if material absorb all light, then color become
All white.
so it shows black. If all color gets absorbed, so material look like black. If all color get reflects, then what happens? All
White.
radiation is reflect, then it is material is look like
White.
white. Yes. And if some is absorb and some is reflect, then what happens? You can have a complementary color. Okay. Some color is absorb or some color is reflect. Then you can have a complementary color. So you can have a complementary color. So what happens in this case? This is just a whip gear. You can just missing I and write down the whip gear. So here see this is a combination. Which color is absorbed and which color is reflected? Suppose violet color is absorbed, then what are the primary color?
Yellow.
Primary
Yellow.
color are
Ye-
primary color are red, blue, and yellow. These three are primary color. Okay, so they are the primary colors. Now see if you can have a combinations. That is, if you like your material is absorbed blue color is absorbed, then it will look like
Orange.
then it reflect orange. So it look like orange. Okay, in this way, if it absorb violet, then it absorb it is having material is look like yellow color. Okay, so in this way you can predict the color. So electronic transition should be take place in the visible regions to show color. Electronic transition should be take place in the visible region to show color. So suppose you may ask question like that, which of the following color light is absorbed by aqueous solution of copper sulfate? Green, it may be yellow, because we know that material is look like blue. So what is your answer?
Orange.
Yes, it's orange. So you can see match appropriate color. So color of Fe, see if you match the following. Suppose you may give one here complex FeNH3 6 times plus 2. You may give one FeH2O6 plus 2 and FeCl6 minus 4, and its color are, you can make the appropriate color, red, yellow and blue. Absorb color. What is absorb color corresponding to red? It is green. Violet for yellow and blue it is orange. ओके सो आपको ये मैच करना है. सो सी कैसे मैच करेंगे? दिस इज सी विप गियर.
Ligand order, always be strong ligand.
Yes, this is a whip gear. So if you go from blue to red shift, what's about wavelength?
Increases.
Lambda is increases. So what's about energy?
Decreases.
Energy is decreases. So see, what is energy order for which ligand having, what is field strength order?
And it's 3
In
greater
field
than,
strength,
it's 2 greater than CL6. CL.
in field strength, you can have a H2O is greater than, see, strongest ligand is a ammonia. The strongest one is ammonia. So the next one is
H2O.
H2O and then Cl. So ligand field strength. Ammonia followed by H2O and then Cl. So highest, lowest energy is for, you can say NH3. So this is, so here say lowest energy means highest wavelength. किसकी wavelength ज़्यादा है?
Red.
सॉरी इसमें जो NH3 है ना तो वो स्ट्रॉन्ग लिगेंड है तो उनकी एनर्जी ज़्यादा होगी. ओके, एनर्जी इज मोर. द व्हाट्स अबाउट वेवलेंथ?
Decreases.
Yes, it is decreases. Good. Wavelength is less.
Blue.
तो
Blue.
ये रेड कलर
Orange.
है. एब्जॉर्ब कलर देखना आपको. सी एब्जॉर्ब, ग्रीन कलर एब्जॉर्ब है, वायोलेट है एंड ऑरेंज है. तो सबसे ज्यादा वेवलेंथ किसकी है, कौन से कलर की है? वेवलेंथ पहले देखो. वायोलेट जो है, उन वायोलेट की वेवलेंथ कम है सबसे. फर्स्ट लेटर है सी. ओके, वायोलेट जो कलर है उनकी वेवलेंथ सबसे कम है. तो व्हाट हैपेंस? वायोलेट कलर इज हैविंग लोएस्ट वेवलेंथ, तो उनकी एनर्जी ज्यादा होगी. सो एनर्जी ज्यादा होगी तो एनर्जी इसकी ज्यादा है, तो इसके साथ आएगा ना, एफ के साथ. ओके, इसी तरह चलो नेक्स्ट जो रेड और ब्लू है, उसमें ब्लू है उनकी वेवलेंथ कम है तो उनकी एनर्जी ज्यादा रहेगी, तो H2O वाला आएगा. H2 एंड Cl, ये दोनों में स्ट्रॉन्ग जो है, रेड कलर की वेवलेंथ सबसे ज्यादा है, दैट मीन्स उनकी एनर्जी सबसे कम होगी ना. ओके, तो कैसे आएगा ये देखना आपको. सी ऑरेंज है, सॉरी ब्लू नहीं ऑरेंज, ये ग्रीन है और ऑरेंज है. तो ग्रीन और ऑरेंज में ग्रीन कलर है उनकी वेवलेंथ कम है ऑरेंज से. वेवलेंथ कम है तो एनर्जी ज्यादा होगी, तो H2O के साथ ही आएगा और ये इसके साथ आएगा. ये चीज आपको कंपेयर करना है. सी ओके, इसको देखना है. इज इट ओके?
Yes, sir.
फाइन. सो दिस कांसेप्ट इज,
अगर लिगेंड स्ट्रॉन्ग है तो
Yes.
वो
उनकी किस
ऐसे
स्प्लिटिंग
को
ज्यादा
लेगा
होगी,
तो एनर्जी कम होगा।
वो एनर्जी ज्यादा एब्जॉर्ब करेगा। एनर्जी ज्यादा एब्जॉर्ब करेगा तो वेवलेंथ क्या होगा? एनर्जी ज्यादा है तो वेवलेंथ
decreases.
डिक्रीजेस। ओके, तो सबसे कम वेवलेंथ है वो है
एनर्जी
फर्स्ट
ज्यादा
कॉम्प्लेक्स।
लेगा तो सर वो उसे तो फिर वॉयलेट को लेना चाहिए था,
नहीं,
सॉरी
पहले
ब्लू
आप
को लेना चाहिए था
पहले आप ये
सर।
बताओ, मैं
एनर्जी
ब्लू है ही नहीं, इस कॉलम को देखना ही नहीं है, वो तो रिफ्लेक्टेड कलर है, कॉम्प्लेक्स कैसा दिखता है वो। आपको ये जो मैंने बॉक्स बनाया ना, ये कॉलम देखना है। सी यू कैन कंसीडर दिस कॉलम,
के
कॉलम नंबर 2।
ओके ओके सर, ओके सर।
ओके, तो इसमें जो कलर्स है वो देखना है। इसमें से सबसे वायलेट फेल है, सबसे कम वेवलेंथ वाला वायलेट है ये कलर। ओके, सो ये सबसे कम वेवलेंथ है। इसका मीनिंग क्या हुआ?
समझ गया सर।
Yes, good. So that's why in this way you can have a different color properties. So this is about transition metal complexes. So now here, see, this is the end of this chapters. Now, is there any doubts till now? Then you can tell me. Otherwise, we
The
stop here.
questions.
Thank you very much.
The questions.